So I am Ankush Bak, Assistant Professor from Department of Electronics and Electrical Engineering, IITGuwahati, as well as I am associated with Center for Nanotechnology, IITGuwahati. So my broad area of research is wide bandgap semiconductor, where we look into the application towards both power electronics as well as optoelectronics. So recently we have made some development towards power electronics, where we developed a high power devices, and the material which we used which has a very wide band gap. Again, band gap, you know, it is a fundamental property of any semiconductor. So, and this band gap decide the application eventually. So this material on which we work recently, the name is gallium oxide, and at the same time we have some technology developed as well as they are commercialized, they namely silicon carbide, gallium nitride. But again, there is of course silicon made power devices, but they all have some limitation considering the high power application, typically traction, ship, then railways, so which requires very high power. But this material, this gallium oxide, due to its very wide band gap, close to 4.9 electron volt compared to the silicon which has, we know, 1.1 electron volt, so it gives us a very high breakdown voltage, which is first and foremost requirement for any high power application devices. And at the same time its on resistance is also very less, so which also ensure it will have these devices will have very low on state losses, and it can also operate at reasonably high frequency. So the primary challenge in this recent research development was to develop this new wide bandgap semiconductor, that is gallium oxide. So this is again another compound semiconductor where both gallium as well as oxygen atoms are there. And here coming to the material development technique, we used low pressure chemical vapor deposition setup, and this is not typically very costly system. So this system we have developed on our own, and it is completely customized. So that is why it has some advantages as well as disadvantages compared to the conventional deposition techniques such as molecular beam epitaxy or metal organic chemical vapor deposition like sophisticated system. But initially we developed this material without doping. Now we know that in wide bandgap or ultra wide bandgap semiconductor, doping is another challenge, because without doping we will not be able to modulate the conductivity of this material, and if we cannot modulate the conductivity of this material, we will not be able to make any devices out of this. So after developing this gallium oxide undoped, then our major task was to incorporate some dopant. And when coming to this dopant part, there are typically different dopant atoms like silicon, tin. So here we use tin as dopant. But again, since this system, that LPCVD system was very customized, so it was little bit challenging to incorporate tin. Because initially we could not get the good quality thin film, because we know that if we want to fabricate the devices from any material, so we need a good crystalline quality material along with the good surface morphology. But when we tried to incorporate tin, it was initially giving some nanostructure on top of its surface, and which is not suitable for making any power device, and of course a reliable and good high performance power devices. And another challenge was initially we observed that we are getting some alloy, so it was not we could get this gallium oxide doped with tin, but we got SN gallium oxide based some alloy, again which was also something not desired for our devices. So after a lot of rigorous study as well as trials, finally we could get the proper process parameters optimized, as well as the setup, our LPCVD setup optimized for getting gallium oxide doped with tin. And after doping with the tin, we could observe that there is a significant improvement in terms of mobility, carrier concentration, which also we could characterize, because since this gallium oxide is ultra wide bandgap semiconductor, typically if we don't dope or incorporate any dopant, we will not get any conductivity. So again, typically to understand conductivity, we need Hall measurement, and initially without doping gallium oxide, we could not even get any electrical contact on this type of undoped gallium oxide. So after tackling this all doping related challenges, we then moved towards the fabrication of devices. So where we fabricated a simple 2-terminal Schottky contact based diode, and we also evaluated its performance, which shows very good performance up to 200 degrees centigrade. So it ensures that this kind of devices not only will operate at very high voltages, but it can also sustain very high temperature, which is also another requirement when coming to the application part, because typically all these devices, power devices, will be exposed to very high temperature environment when it will be under some operation. So considering this, we are still working, and we are now looking for to develop some 3-terminal devices such as a transistor, and we are towards that. So as I just explained, so to synthesize or develop this gallium oxide based material, so we used this kind of low pressure chemical vapor deposition setup, and as you can see, this is completely customized. So here we bought different component and then assembled together as per our requirement. Now this is the main furnace. So inside this we have some boards, and on the top of board we kept the gallium as a precursor, and there is another gas cylinder attached to after these MFCs. So this oxygen is another precursor to develop this gallium oxide material, but we also use this argon as a carrier gas. So now this both argon and oxygen gases are coming through these MFCs, and inside we have this gallium metal itself as a precursor, and on top of this gallium metal and along with some other arrangement, so we kept our substrate, and the substrate is the sapphire we used for this particular study. So initially we got the undoped gallium oxide thin film on the sapphire substrate. So and after that we used another board where we kept this tin as a dopant, and then after, as I mentioned earlier also, initially it was very difficult to get tin incorporated in this gallium oxide material. So but after a lot of trials and rigorous study, we could ensure that there is a incorporation inside this gallium oxide material as a dopant. So this is the setup that you used during that material development. We used this kind of transparent sapphire substrate to develop this material. So this is again a 2-inch sapphire substrate. So again, although as I mentioned, that growth system or material development system was completely customized, so we had to use a small portion of this substrate. So we could not use this entire 2-inch substrate to develop this material. So after developing this SN doped gallium oxide good quality crystal quality thin film on this type of substrate, we fabricated 2-terminal devices, such as Schottky barrier diode, and those diodes we characterize using this kind of probe station as well as this source measure unit. So this source measure unit, this is again another electrical characterization equipment. So it provides very high voltage. So this is a different model. So it can provide up to 1100 voltage, which is again required when we are characterizing different typical power devices. And here we are keeping this SN doped gallium oxide thin film after fabrication of the diode. So we just put so this is again just for demonstration purpose I am showing. Here we do not have any gallium oxide or SN doped gallium oxide thin film grown. So but during that experiment we grew those gallium oxide on this kind of sapphire substrate, and we fabricated devices, and after fabricating the devices we used this kind of probe station. So here these are the two terminals. So again, as I mentioned, we could fabricate simple two terminal Schottky barrier diodes where we have one anode and another cathode. So and these are the probe tip, and this is called the chuck, and it also ensures that you will be able to measure this device terminal characteristics at very high temperature. So similarly, this the chuck temperature can go up to 200 degrees centigrade, which is again a very important parameter for typical power device applications. So I should also acknowledge and thank my students because they were the key for this research development, and primarily two of my PhD students, Manoj Kumar Jadhav and Arnab Mandal, so they took the lead for this research. So Manoj Kumar Jadhav, he already completed his PhD, so he developed the device part, and Arnab Mandal, he is still pursuing his PhD, so he developed that material. So in that way, so they both contributed a lot for this gallium oxide based power devices research. And finally, I also would like to acknowledge the funding support that we received from Science and Engineering Research Board, that is SERB, Department of Science and Technology, Government of India, and I also like to thank all the other necessary support we received from both Indian Institute of Technology Mandi as well as Indian Institute of Technology Guwahati to conduct this research on power devices. Thank you.